Good evening, students. Am I audible? You just have to tell me if I'm audible. Yeah, yeah, fine. People are saying that I'm audible. Fine. Let us start. Yeah, good. Now, this week we will start with the instruction site. Till the previous week, we discussed about different register organizations, right? We discussed about general register organization, we discussed about single accumulator organization, and we discussed about stack organization. Today, I'm going to give you the complete insight view of the instruction cycle. You people knew that the computer system, when it comes to the CPU, does nothing other than instruction execution. When it comes to the computer system as a whole, it is going to execute the programs, right? But when it comes to the CPU level, it is going to deal with instruction by instruction. It is going to get the first instruction of a program. It is going to decode it, execute it. It is going to go through all the phases of this instruction. After finishing with that specific instruction, it is going to go to the next instruction. Yeah, good evening, Lokesh Parab. Now, what I am going to do is, I am going to give you the complete insight view of an instruction cycle. How an instruction will be fetched, decoded, and executed by the CPU. Let us stay focused. Arjit, Swati, good evening, good evening. Let us get into the details. The instruction cycle. Yeah. Today's session, we are going to deal with two things. One is instruction cycle and one more is flag register. Okay. I want you people to participate. When I do have a question, I want you people to completely participate with me without having any doubts in your mind. If you do have a doubt, shoot. Do not wait for the things to happen. Let us initiate the things to understand completely what I'm explaining here. So today's class is all about, today's session is all about instruction cycle and the flag register. Alright? Yeah. Kirti, hi. Swati, hi. Arjit, hi. Lokesh, hi. Let us start. Okay. Now, you know that when it comes to a computer system, we do have a register set, control unit, and the ALU, right? We already discussed about the register set and control unit and ALU. Sorry, ALU we're going to discuss in the upcoming classes. Control unit and the ALU we're going to discuss in the upcoming classes. Okay, now we are going to deal with the instruction cycle. For that, first of all, we need to understand how an instruction is going to look like. Yeah. Now, first of all, for everything in a computer system, there will be a specific size. There are a few new guys who joined. For them, just let me give you a 2-minute introduction to the register set. What do we have? Okay, so in fact, we are dealing with single accumulator organization. When it comes to the registers, we are using single accumulator organization. Let us stay focused what we are dealing with. Okay, so we are talking about, so far we discussed about a register set. Okay, let me, it is taking some time, just a moment. Yeah, we discussed about a register set. Okay, let us in the register set, any organization you take, the one of the important register in the register set is instruction register. Okay, I'll call it as IR. What is instruction register? When it comes to the instruction register, this instruction register is going to hold the current instruction that is getting executed. That is, any time when we have a look at the CPU executes some instruction all the time. If you can press a pause button if it is there and open the CPU, and if you can have a look at that CPU, you're going to witness that CPU executes one instruction at that particular point of period. The present instruction, the current instruction which is being executed by the CPU will be there in the instruction register. Okay, here in our architecture, the sample architecture that we are discussing, the example architecture we are discussing, the instruction register size is equal to 16 digits. Okay, the instruction register size is equal to 16 digits. Alright, which means that the instruction size is equal to 16 digits. Okay, instruction size is equal to 16 digits, meaning my instruction in my architecture is of a size which is equal to 16 digits. Let us examine these digits. Okay, now let me draw a block diagram of instruction register. Pardon my drawing. Okay, let us feel that this is my instruction register which is equal to 16 digits. Okay, now the instruction register will get divided into two primary fields. Take any architecture. When it comes to the instruction will have two different fields. Rather, it is divided into two fields. One field is called Opcode Field. I'll label it as OPC. Is it clearly visible? Lokesh Parab, instruction register, it is not the point to the next instruction to execute. You're talking about program counter. Okay, program counter is going to point the next instruction that is going to get executed. But when it comes to the instruction register holds the current instruction that is being executed. Is that fine? Okay, now the total instruction will get divided into two fields. One is opcode field and second one is address of the operand. I will call it as ADD, stands for address operand. Okay, that is my instruction has been divided into two fields. One is opcode field and the second one is address of the operand. Okay, now what is this opcode field and address of the operand field? Let us understand. You know that if you want to execute an instruction, we do require an opcode. Yes or no? Let us have a discussion here. Kirti, do you know that we do require an opcode for executing any instruction? Tell me. Swati, Kirti, or whatever. Arjit, do you know that we do need an operand? We do need an opcode? Or Lokesh, just answer me. Yes, good. So here, the total instruction register, if you can have a look at, there is an opcode field, right? This is an opcode field. This is going to contain an opcode, right? Now, very good. Now, I do have another question. If you do have an opcode, we do require an operand also, right? The opcode is going to present an operation. It is going to give you an operation which is going to be performed on a particular operand, right? Yes or no? When you have an opcode, we do also need an operand. Am I right? I want answers. Good. So we do require an opcode as well. We do require an operand. This is what my instruction register does contain, an opcode and an operand. Now, Kirti Kumar, operand to perform a specific operation. Very good. I do have another question. Now you just answer the questions which I pose so that you are going to understand to the depth of the architecture it is actually required, okay, to crack any exam. Forget about exam, forget about gate exam. There won't be any gate level. There will be only a subject level. If you can masterize any subject to the level it is required, then any exam will follow. Did I make it myself clear? Yeah. Now, if you have an opcode, how many operands we do require generally? Let us take an arithmetic operation. If I want to perform an arithmetic operation, minimum how many operands that I do require? Kirti or Lokesh or whoever it is here, whoever those are present in the class. Yes, Kirti, I do require 2 operands, right? I want Lokesh also to talk. Arjit and Swati, there are several people. Excuse me, I do require only 2 operands. Ajit, I don't require 8 operands, okay? I don't know why did you press 8. Very good. Lokesh, I do require 2 operands. You want to perform addition. If you want to perform an addition, how many operands do you require? 2 only, right? It's a simple question. It's a simple mathematical logic. I'm not taking you into architecture. It's the simplest question which can be answered by even a first class student. So, if you want to perform an arithmetic operation, we do require 2 operands, right? Let us stay focused. In this context, let us say that this opcode, let us say it is add. Okay? This opcode is going to perform addition. Okay? Forget about this address of the operand. Okay? Forget about this. This field is going to give you one operand. Okay? Are you understanding? Are you getting it? I'm going to perform addition. If you want to perform an addition, I do require 2 operands. Here, this field, which is an operand field, actually it is going to give you an address of the operand. I'm going to get into the details what is the address of the operand. But for an instance, at this point of period, just try to understand that this field is going to give you an operand. Let us say that is 450. Okay? Are you getting it? Good. Now, I'm performing an operation that is addition, which requires 2 operands. In our case, we do have only one operand. Okay? We do have only one operand. Then what is the second operand? Simply I can't add 450 to the space, right? I do require another operand. Now, let me get into the architectural details here. How do I get a second operand? Now, in this current architecture, that is single accumulator organization architecture, the second operand is always accumulator. You know accumulator, right? Kirti or Lokesh or Ajit or Swati, whoever you are. Accumulator is a register, right? Yes or no? Answer me. Am I making it myself clear? You hear? All of you guys are sleeping. Yes, accumulator is a register. Here, in our architecture, when any instruction is going to get executed, that instruction is going to have an opcode in the instruction and one operand within the instruction. The second operand is always accumulator, which means that here, after executing this instruction, the result is accumulator is equal to accumulator plus 450, which is given in the instruction itself. That is, accumulator will always be the implicit operand for every instruction, because in the instruction we do have only one operand. Okay, and the second operand we do require, that is always accumulator in the single accumulator organization. Did I make it myself clear? see, Lokesh Parab, you are talking about 8086. Several times I told you that in 8086, accumulator is AX register. But in our architecture that we are discussing, which is single accumulator organization, accumulator is called accumulator itself. I don't call it as AX. But when it comes to the 8086, of course, accumulator is called AX register. Okay, so do not get the other things here. I'm not discussing about 8086 architecture. Okay, 8086 architecture follows general register organization. We are following single accumulator organization. Did I make it myself clear? Yeah. Okay. Now, in our the architecture, second operand is always accumulator. That is, when an instruction is getting executed, it is going to perform the operation which is specified by the opcode in between two operands. One operand will be given by the instruction. Second operand will always be the accumulator. So, as the output of the instruction, as a result of the instruction, the accumulator will get updated. This is the thing. If you can understand this, I will take you to the next level. Did I make myself clear? Okay. Shall we go to next level? Yeah. Now, see, again, let us have a look at the instruction register. The instruction register, as I told you, it is going to have two fields. One is opcode. Second one is address of the operand. Okay. Here, opcode is anyhow addition or subtraction or whatever. I'm not talking about the opcode here. Okay. Here, in the instruction, within the instruction, this operand field is going to specify most of the times the address of the operand which is available in the main memory. Okay. For an example, most of the times if I say 450, 450 is not the direct operand. Rather, 450 is a memory location. 450 is a memory location in which the actual operand is available. Okay, most of the times the instruction is going to specify in the address of the operand field an address which holds in the main memory the actual operand. Okay, the address, the operand field is going to hold an address, a memory address in which the actual operand is available. Okay, that is, whenever an instruction is getting executed, this operand field is going to present you an address. What address it is? It is a memory address. Okay, this 450 is a memory location's address in which the actual operand is available. As a result, this instruction, the result will be equal to, accumulator is equal to accumulator plus M of 450. Okay, memory of 450. What is memory of 450? Memory of 450 is 150. The contents of the accumulator will get added to M of 450, which is equal to 150. Finally, the accumulator is equal to accumulator plus 150. Yes or no? Yeah, sure. I'm going to explain. Unless you understand it completely, we are in no hurry to move forward. Okay, I will show you. No, I'm not saying the 450 is the result stored in the memory. Okay, let me show you here. So stay focused. Lokesh Parab, are you here? Okay, this is memory. Okay, this is my main memory. This is my main memory. Okay, in main memory, let us say that there is a 450 address. In 450, the actual value is 150. Here 450 is an address. Right, Kirti? Are you sure, Kirti? I want answers. I want answers. This is main memory. Good. Stay focused here. My main memory size is equal to 4096 words. Okay. Total main memory size is from here to here. This is 0th location, and excuse me. And the final location is 4095. My main memory size is equal to 4096 location. One of those location is 450, which is nothing but an address. Okay, which is nothing but an address. Okay, so here when it comes to instruction, the instruction will have two fields. One is opcode plus second one is address part of the operand. Okay, operand. Opcode field is going to specify the opcode, that is, let us say, addition for this instance. In addition to the opcode field, we do have an address, add 450, which means that this field is going to give you a memory address. Okay, taking which we need to go to the main memory. Okay, under which there is an actual operand that will have to be added to the accumulator. That is, as a result, accumulator is equal to accumulator plus memory of address part of the operand, that is 450. Okay. Finally, let us say accumulator is equal to, there is an accumulator register currently 160. Okay. After executing this instruction, accumulator will get updated to 160 plus 450. If I am not wrong, that is equal to 610. Did I make it myself clear, Kirti? Or do you need one more explanation for this? Okay. So every time when an instruction is going to get executed, we do have an opcode, of course. In addition to the opcode, we do have an address field which will give you a memory address, taking which we'll have to go to the main memory. Do not think that the 450 is a direct value. Okay, there are a few exceptions. We are going to talk about those exceptions later. But at this point of period, strictly, this field is going to give you an address part of the main memory. Okay, taking which we need to go to the main memory. Okay, when we go to the main memory, under this location, at this location, under this address, there is a value. Get this value to the CPU. Okay, and that value will be added to the accumulator. This is how an instruction is going to be interpreted, and an address will be fetched out of the main memory. Finally, we will get the value, and finally, we are going to perform the operation. Every time, the only thing needed to be remembered here, two important things. In a single accumulator organization, in our case, in addition to the opcode, we do require two operands, right? One operand is always accumulator, forget about it. Second operand, who is the second operand? Second operand will be most of the times available in main memory. If you want to go to the main memory, what do you need? We do require an address part, right? That will be specified in the instruction, which means that add 450. This is an instruction register contains add 450. This is an opcode, and this is the address part of the operand. Did I make it myself clear? Yes, these are the basics operations of the. I can't say these are the basics of the basic operations of the computer. These are the very operations of the computer, the main operations of the computer. Because what is a computer system? The computer system is going to execute the instruction. These are the very important activities and the operations of the computer system. Did I make it myself clear? These are not basic. There is nothing basic or advanced. we have to figure out. Okay, there is a puzzle here. Is a puzzle difficult or complex? No, there is no such word as a difficult or complex. Puzzle has to be resolved. We are tracking the details one by one. Finally, we are going to have the complete dish in our hand. Okay, these are the footsteps. But let me tell you, these are the very operations that you need to understand to have a better idea, to have a complete idea about the computer architecture. Very good. Okay, now I am going to take you to the very next level. So far what did you learn? All of you guys who are sitting there, there is an instruction register. The instruction register having two fields. One is opcode, address of the operand, right? Okay. Here, let me take you to another level here. That is, actually, so far we discussed about the opcode. The opcode is going to give you the operation code which is going to be performed on the operand, right? Finally, this opcode will also be divided into two more fields. So far we discussed simply. Now let me give you a complete idea how an instruction is going to look like. Generally, the total 16-bit, right? Instruction register is equal to 16 bits. Because one word is equal to 16-bit in our architecture. Yes or no? Several times we discussed that. One word is equal to 16 bits. Which means that a memory location size and any register size is equal to 16 digit, right? We're following 16-bit architecture, 32-bit architecture. What does it mean? You got it? One word is equal to 16 bits in our architecture. Let us say that you bought i9 or i5. The vendor is going to tell you that this CPU is a 64-bit CPU. What does it mean? It is not a biggest deal. In that CPU that you bought, one word will be organized as 64 bits. That's it. A memory location is equal to 64 bits. If you want to have a memory location, 8 bytes you require. One word is equal to 8 bytes. But in our case, one word is equal to 16 bits. If it is 16 bits, every location is 16 bits. Every register size is equal to 16 bits. Apart from those registers which holds the addresses. Okay, now forget about it. The instruction register size is equal to 16 digits. Okay. This address of the operand will be equal to 12 digits because it is going to give you a memory address. Yes or no? When it comes to a memory address must be equal to 12 digits because main memory is equal to 4096 words. Yes or no? My main memory size, the main memory size what we have taken is 4096. 4096 is equal to 2 power 12, which means that memory require 12-digit address to represent any of the locations. Did I make it myself clear? Did you understand this? Good. Memory require Lokeshwara? Yes or no? Memory requires 12-digit address. Yes or no? Good. So memory requires 12 digits address. As this address of the operand field is going to present you a memory address, so this must be equal to 12 digits. How many digits that are left? 4 digits, right? So here the opcode field, the actual opcode field is equal to 3 digits, and there is an additional field called mode field. This is mode field, this is opcode field, and this is the address of the operand field. So already you know what is opcode and what is address of the operand. Now there is a new guy. We got a new guest here. Who is this guy? This guy is a mode. He is going to give you an addressing mode. What is an addressing mode? It is not a biggest deal. I will make it very simple if you concentrate. Yeah, I'm exactly there. Stay focused. Mode field will tell you in what way this address should be taken. Mode field is 1 digit. So how many modes are possible? 2 modes, right? Kirti, answer me. If there is a 1-bit mode field, how many modes are possible? 2 modes. If the mode digit is 0, there is one mode. If the mode digit is 1, there is another mode. Yes or no? 0 represents something, 1 represents another thing. I want answers. Very good. So, try to understand, if the mode field is 0, it's a direct address. If mode field is 1, it's an indirect address. Sir, what is direct address? What is indirect address? Don't worry. We are talking about the very address of the operand. We are talking about this address of the operand. How to get this address of the operand? Okay. If the mode digit is equal to 0, the address of the operand is going to give you a direct address. If the mode digit is equal to 1, the address of the operand is going to give you an indirect address. Don't ask me what is an indirect address. Indirect address is a pointer. Pointer means the address, this field is going to specify an address in which there is another address. Did I make it myself clear? No, Lokesh. Once again, very good. You knew a few things. I'm not talking about base register or an index register. From now, exactly the 3rd week, I'm going to talk about the addressing modes. Okay, from now, exactly the 2nd week, I'm going to talk about the addressing modes. In the addressing modes, you are going to understand what is base address, what is index address, what is an offset address, everything you are going to understand. Did I make it myself clear? Very good. So, I'll tell you, okay, 0, add 450. If it is 0, add 450, this field talks about the address field. Okay. If it is 0, 450 is the direct address. Go to 450. Okay. Get this value, get it added to accumulator. Okay. Otherwise, if it is 1, add 450, which means that this is an indirect addressing mode. The address part of the operand is going to specify an address under which there is one more address. Here, under 450, in the indirect addressing mode, we do have one more address. This cannot be the operand directly at that time. This will be one more address in which the actual operand is residing. Did I make it myself clear, all of you guys, or you do require one more explanation? Under 150, there is, let us say, 200. This is the actual operand in the indirect addressing mode. Okay, Kirti, then if it is mode 2, which type of address is it, sir? Yeah, that is what I explained you, right? It's a mode 2. What is this? This is mode 1. First mode is 0. Second mode is 1. It's a direct addressing mode. Yeah, good. You answer me. You answer me. You answer me, Kirti. My questions are to you. Just type it as I ask, so that I will be able to know how you are going to get it. What is the instruction? Add 450, right? If it is add 450, 450 is going to give you an address, right? Okay. Now consider that. Here is my question. 0. First bit is 0. This is 0. 0 add 450. If it is 0 add 450, anyhow we are going to main memory or not? Anyhow we are going to main memory or not? Tell me. My question is, 450 is the memory address. Yes or no? What is 450? Tell me. I am not getting any answers here. Very good. 450 is nothing but an address, right? Stay focused. It's not a big deal. 0 is a direct addressing mode. 450 is a direct address. When it is 0, go to 450, get the content under 450. What is the content? 150, right? That is the operand. When the addressing mode is 0, because it's a direct address. The address part of the operand is going to give you an address in which the operand is available. But when the mode bit is equal to 1, it is going to specify an indirect addressing mode. In the indirect addressing mode, the address part of the operand is going to have an address taking the address will go to the main memory. But under this, the value is not the operand. The value is another address. Okay. Under that specific address, there is an operand. Yes or no? Did you understand this? So, finally, in the direct addressing mode, the accumulator is equal to accumulator plus m of 450. Okay. This is 0. Okay. Direct addressing mode. When it is equal to 1, accumulator is equal to accumulator plus m of 450. That is, m of 450 will give you an address 150. Okay. Is 150 the value? No, 150 is not the value, because addressing mode is going to give you, addressing mode is giving us the indirect addressing. Okay, so m of 450 is going to give you 150. Okay, m of 150 is going to give you the actual operand, that is 250. 250 plus accumulator. Did I make it myself clear? Did you understand this? You guys? What is no? Good. I got it. It is not the direct operand, rather it is an indirect operand. Did I make it myself clear? Good. Now hold on. I am going to take you people to the very operations that are going to be performed when an instruction is going to get executed. Okay, are you there? Good. Yeah, you able to see this? This is what I exactly told you guys, right? Do you getting this? Yes or no? Now stay focused. Here the things what I explained are being showcased. Here we do have a main memory. Main memory is of 4096 bits. That means that the address part is equal to 12 and the word part is equal to 16 bits. Okay, and mode digit 0 is the direct address, 1 is the indirect address. Yes or no? And the opcode is 3 bits. When we do have a 3-digit opcode, the maximum number of opcodes that we can have is 8. Yes or no? Kirti, I do have a 3-bit opcode. How many maximum opcodes are possible in our architecture? 8, right? 2 power 3 is equal to 8. Am I right or wrong? Lokesh and Kirti, tell me. Eight, right? Very good. Now, see here. Stay focused, all of you. Stay focused, all of you. This is the very thing you do require. If you want to crack gate in computer architecture, you do need to understand these things. Let it take time, doesn't matter. Okay, but I want you guys to understand completely. Okay. Now, what is PC? What is this register PC? PC stands for what? Kirti and Lokesh, what do you mean by PC? What do you mean by PC? PC stands for program counter. Very good. What is program counter? Address part of the next instruction, right? Program counter will hold the address part of the next instruction. Very good. Now stay focused. What is address register? Here this is address register. Let me tell you, let me give you a small recap of all these registers. See, every time when you want to go to when you have to go to main memory, you do need an address, right? When you need an address, that is not enough. That address must be transferred to the address register, because address register can only communicate with main memory. Address register is the only register that can communicate with the main memory. So if you do have an address that needs to be taken to the main memory, that needs to be located within the main memory, that address must be transferred to the address register, because address register is the mediator between main memory and the CPU. Okay, so that is what address register is all about. I don't want to talk about instruction register, because you know what is an instruction register. Yes or no? You do know what is an instruction register. What is data register? The data register is going to hold the current operand of the instruction. That is, in our case, we got an address 450. Yes or no? Under 450, there is a value 1050. Data register is going to hold the current data operand which is specified by the instruction. Okay. Anyhow, one operand is accumulator. We can't change it. Accumulator is all the time one of the operand. That is an implicit operand. Second operand must be transferred to the data register, because finally the operation is going to be performed in between accumulator and data register. Are you listening? First of all of you guys. Kirti? Lokesh and Kirti. Am I audible? I'm not. Good. So, now stay focused. What is data register? Understanding data register is important here. What is data register? Finally, the operand after address has been located within the main memory, there is an operand. The operand must be fetched and should be transferred to the data register for the final execution. Okay. Anyhow, one operand is accumulator. Second operand must be transferred to the data register. Finally, the operation is going to be performed in between accumulator and data register. Did you understand this? Good. Now, let me take you to the instruction cycle. Now, the current instruction is 22 that is being executed. Okay. Just talk to me. That's it. You talk to me. We're going to complete it within a while. Okay. The current instruction is being executed. The current instruction is available in the instruction register. The current instruction is 22 and the next instruction is 23. That is, next instruction address is 23. As the next instruction address is 23, that will be held by the program counter, because the definition of the program counter itself is holding the address part of the next instruction. Fine? Fine, exactly. Kirti, you are right, exactly. What you interpreted is correct, because any operation must be performed in between two processors register. I cannot perform the operation in between a memory location and a processor registers. First of all, take any organization, i9, i10 or i11 or i100 or i3, Celeron, take any architecture. If you want to perform an operation, first of all, the operand must be made available within the processor. Anyhow, one operand is accumulator. Second operand must be brought into the CPU's registers. The register is data register. The intermediate register is data. I can't say intermediate register because technically it is wrong. But at this level, I can tell you that data register will act as an intermediate register to store the current operand. Okay, but do not think that the data register is an intermediate register. Okay, so at this point of period, what you interpret is exactly right. Fine. Okay, now instruction register is holding the current instruction which is available in 22. The next instruction is held by program counter. Okay. Yeah. Let us say that current instruction is executed. As the current instruction is executed, I did not come to that level. E, I will tell you, do not supersede me. There is something called E, which is called extended accumulator, but I did not come to that far. You're going to understand. Let me give you an assurance that you're going to understand every single little detail if you follow my classes carefully. That's it. Okay. Now, where am I forgot. Fine. Program counter is holding the address part of the next instruction. As it holds the address part of the next instruction, when the current instruction gets executed, we need to get the next instruction into the instruction register, right? Yes or no? Answer me. Current instruction is executed. What is our job? What is our job? We need to get the next instruction into the CPU, right? Yeah. So what we do is, program counter holds the address part of the next instruction. Taking this address, we need to go to the main memory. But can we go to the main memory directly? Can the program counter mediate with the main memory? No, program counter cannot mediate with the main memory. There is only one register that acts as a mediator between CPU and the main memory. That is only address register. Okay. So for that reason, the program counter value must be transferred to the address register. Why? Because I do have an address. I do have an address, taking which I need to go to the main memory. But program counter cannot go to the main memory directly. Okay. If you do have an address, and when it has to get located in the main memory, please transfer to the address register, because address register will take care of talking to the main memory and getting the contents for you. You got me? Very good. So for that reason, program counter to address register transfer will happen. This is the first thing that is going to happen in every instruction cycle. After executing the current instruction, the first thing that will always happen in every architecture is the contents of the program counter will get transferred to the address register. Alright? Very good. Now stay focused. Address register holds the address of an instruction. Okay. The moment address register gets an address, immediately that address will be located in the main memory and the content will get transferred to the instruction register. Again, program counter value will get transferred to the address register because address register is the only register that can talk to the main memory. The moment address register is loaded with an address, immediately that will get located within the main memory and the content will get transferred to the instruction register. You got me? Did you get it or not? Want answers? Good. Now, there is a small exception. Here, the content of the address register, let me put it in other words. Address register can hold two different addresses. Rather, there are two different addresses that can be available, that can be transferred to the address register. Address register can hold instructions address or an operand's address. If it is an instructions address, then the content will get transferred to the instruction register. If it is an operand address, then the contents will get transferred to the data register. Did you understand? You got me? If the address register contains an instruction register, then taking that address, main memory will get located, under which the content, as it is an instruction, it will get transferred to the instruction register. Okay. If the address register contains an operand address, taking which we will go to the main memory, as it is an operand, then the content will get transferred to the data register. Did I make it myself clear? Good. Okay. Now, initially, as a first thing, as the instruction is getting executed, initially address register is going to hold the instructions address only, because in the beginning we don't have an operand unless the instruction has been transferred to the instruction register. Okay, in the initial phases of the instruction cycle, address register will always hold the instructions address. Once after instruction register is filled with the data, then we can get an operand address. Okay, now next instruction is 23rd instruction. 23rd will get transferred to the address register, under which there is an instruction, that instruction will get transferred to instruction register. Got me? Now you can clearly see this. You can clearly see this. Okay, this is the instruction. There is an opcode. Sorry, there is an mode. There is an address of the opcode. Sorry. Just a concentration problem. There is a mode, there is an opcode which is nothing but addition, and there is the address part of the operand. Right? Now, here stay focused. This is the current instruction that is needed to be executed. This is the current instruction that is needed to be executed. What is the opcode? Addition. And where is the operand? One operand is always accumulator. We don't need to talk about it. And the second operand is available here. Is this the direct operand? No. It is an address, right? What kind of an address? It is an indirect address. Yes or no? So anyhow, no matter whatever it is, as it is an address, it has to be located in the main memory. Yes or no? It has to get located in the main memory. If you want to locate it in the main memory, can the instruction send the addresses to the main memory? No. Which register can send the addresses to the main memory? Only address register, right? So, as a next thing, this 450 will get transferred to the address register. You got me? Very good. The moment address register is loaded with an address, immediately that will get located in the main memory. Now it is not an instruction. It is not an instruction, right? If the located address holds an instruction, that will get transferred to the instruction register. But the located address is not holding an instruction. Now the located address is going to hold an operand. So for that reason, this will get transferred to the data register. Yes or no? For this reason, this will get transferred to the data register. Stay focused here. Stay focused if you are listening. Okay. The mode bit is 1, right? If the mode bit is 0, then it is a direct address. 1050 is the actual value. 1050 plus accumulator will be the final answer. But now the mode digit is showing 1. What does it mean? It is an indirect address. Indirect addressing means 450 holds an address. 450 holds an address under which there is one more address. 450 holds an address under which there is an actual operand. So for this reason, this 1050 will get transferred to, 1050 again will get transferred to address register. Under 1050 there is 750, that will get transferred to the data register. Finally accumulator is equal to accumulator plus 750. Okay, let us once again stay focused. Program counter will get transferred to the address register. Under the address register, that is what, Kirti, it is not direct address. Under the address register there is an instruction. The instruction will get transferred to the instruction register. Now imagine that it is 1, that is indirect address. In the indirect addressing mode, the address part of the instruction is going to contain an address under which there is one more address. So here, but anyhow, the address is an address. If you want to locate that address into the main memory, the address should be initially transferred to address register. Again, the moment address register is loaded with an address, immediately the content will get transferred to the data register. For an instance, it will get transferred to the data register. Okay, but again the data register will send this value back to the address register because 1050 is not the value. 1050 is an address. Okay, so 1050 will get transferred to the address register. If it is the direct value, there is no problem. Finally, accumulator is equal to accumulator plus 1050. But now this 1050, as it is not the direct value and an address, this will get transferred to the address register. The moment address register is loaded with an address, immediately that will get located in the main memory, under which the content will get transferred to the data register. Finally, accumulator is equal to accumulator plus 750. Did I make it myself clear for both of you guys, or you do require one more explanation? Kirti and Lokesh. No. Very good. As it is 750, see, listen to me Kirti carefully. When an address has been sent to the data register knew that it is an address and it will get sent to the address register. Now when a value is sent to the data register, why it would send it to the address register? As it is already a value. Okay, and anyhow, to make it precisely, if I am a data register, I won't be able to distinguish between address and the data. Let us stay focused, all of you. Kirti, stay focused. I am the data register. For me, I am a register. I can hold whatever it is sent to me. But there is something called a control unit. The control unit will decide what will happen to the data as it is transferred to me. Once the data is transferred to me, the control unit will decide. If an address is transferred to me, then control unit again will get it transferred to the address register. When a data element has been transferred to me, the control unit will not make any transfer here because already data element is present. The data operand is present. The control unit will take the subsequent steps to perform the operation. Yes or no? You got me? Kirti, as it is already 750, the 750 as it is not an address, why would address register send it back to the address register? No need, right? Good. This is how an instruction is going to get executed. Now stay focused. I am going to answer your question, Kirti. What is C? Okay. I talked about C, right? What is, E. E stands for extended accumulator. Okay. What is extended accumulator? To make it precise, to make it clear, accumulator is a 16-bit register, right? Accumulator is a 16-bit register, right? But can you give me a guarantee that result will also be within 16 bits? Not possible, right? Here all the registers are equal to 16 digits. Accumulator, data register, instruction register are of 16 digits. And the address register and the program counter are not 16 bits, are only 12 bits. Are of only 12 bits because these are going to hold the addresses. Forget about that. Here what does matter is data register size and the accumulator size. Data register size is equal to 16 digit. Accumulator size is also equal to 16 digit. So, to 16 digit values are being added. If this is the case, the result cannot be guaranteed to be within the 16 digits, right? The result can be of 17th digit also. Sometimes there may be an overflow. Sometimes there may be a carry or overflow, whatever you call. Okay. When there is an overflow, that overflow will get directly accommodated in an extended accumulator which is equal to 1 digit. Did you understand this? Yeah. So, the result can be sometimes more than that of the size of the accumulator. So, at that time, in order to accommodate this carry, we do require an additional register. This additional register is extended accumulator. Okay. If you could recollect your 8086 architecture, there is something called EA. What is EA? EA stands for extended accumulator. Okay. Here, extended accumulator is only 1 bit. Okay. Sir, you have one 16 digit and another is 32. Kirti, stay focused. There won't be any overflow. If a 32-bit value is getting added to 16-bit, what is the chance of overflow? But here we are not talking about a 32-bit architecture. We are talking about just 16-bit architecture, which means that the maximum size of an operand is 16 bits. Look at the main memory. What is one location size? 16 digit. If it is 16 digit, obviously all the register size must be equal to 16 digit. There is no 32-bit register present in our architecture. Then let us take a 32-bit architecture. If you want to update your processor from single accumulator to 8086, rather from the single accumulator to Celeron processor or Pentium processor. Pentium processors are 32-bit processors. So at that time, data register will be equal to 32 digits and the accumulator is also equal to 32 digits. Did you get it? At that time also there might be an overflow. What is that? When two 32 digits are getting added, the result might be a 33 digit result. Okay. Most of the times it will be well within the 32 digits, but sometimes when the result is sometimes extended, we may get a carry. The carry will directly get accommodated into this extended accumulator because there is no such guarantee that when two equivalent digits values are getting added, the value also within the same digits. Okay. So we do require an extended accumulator. Did I make it myself clear for you guys? Yeah. Already it is 7 o'clock. I didn't look at the time. Fine. Anyhow, I'm going to continue this in the very next class. Okay. Obviously, I think you knew this. Now you understood this. Okay. If you understand this, let me give you an assurance that the computer architecture will be a simplest subject from the next class onwards. Did I make it myself clear? Sounds good? I'm taking a break for 1 week. So next class will be same day, same time, next week. Data register must also have extended. No, result will always be within accumulator. Data register doesn't have an extended value. Data register, why it don't require an extended value? Because all the time result will get stored in accumulator. Finally, the register which holds the result needs to have an extended register. But in most of the advanced architecture, all the registers are provided with extended registers. Why? We are going to discuss later. Not to store the result. Okay. There is a specific purpose to extend even the data register. Okay. So we are going to understand about all such things in the upcoming sessions. Okay. Till then, take a break and enjoy your remaining sessions. Okay, fine. That's it for the day, and I'm going to end the session right now. Thank you, guys.